Mathematics is never wrong. When a proposition is true, it has irrefutable proof behind it. But what happens when the theorems become complex and their proofs look incomprehensible? You can't be sure anymore. Mathematicians can get tired, misread things, and make mistakes. You know who doesn't though? Computers. Please, a calculator isn't real math. You're telling me that a computer program can not only represent all of math but even verify it? Computers can only check if a number is prime or not. Can it verify that infinite primes exist? Yes, they're called proof assistants, and they've been all over the news recently. And guess what? They do that by just type checking. That little thing which stops you from assigning a string value to an int variable, which throws an error for returning a boolean when the function's return type is float, yeah, it can also catch errors in your proof. Are proofs and programs related? Let's find out. Propositions are statements that can be true or false. If they're true, they have proof, which could range from extreme rigor to divine revelation. That's why we developed a formal system with axioms and rules that can be checked unambiguously, like chess and its rules. The axioms of math are like the chess pieces' starting positions. These are assumed to be true. The rules of logic in math are like the rules for moving the chess pieces. These help us construct other true statements. In other words, any chess position is true if it can be reached from the starting position via valid steps. This valid sequence of steps is its formal proof. On the other hand, positions which cannot be reached from the start are false. Of course, changing the starting chess position changes what is true and false. We can formally represent chess using algebraic notation or the 8x8 chessboard. This should instill some hope in us. Chess can be understood by a computer and its rules verified. Can math also be written formally? These symbols along with variables get the job done. There are infinite primes is formally written as for all n of type nat, there exists a p of type nat such that p is greater than n and p is prime. That is, for any natural number I pick, there will be a number greater than it which is prime. And since the natural numbers go on till infinity, so will the prime numbers. We can break these down even further. P is greater than n is defined as there exists an x of type nat such that p equals n plus x and not p equals n. P is prime is defined as p is greater than or equal to 2 and for all natural numbers m divides p implies m equals 1 or m equals p, which means the only divisors of p are 1 or itself. You don't have to understand all of this, only that most math can be written using these. Mathematicians cover these up with simple language and definitions. You will also notice the exists and for all symbols in Lean's logo. Speaking of Lean, let's check out Lean's type checker in action first. Every object in Lean must have a type. This notation is used to express this fact. Using the check command on 2 tells us that 2 is of type nat. Using it on math tells us math is of type string. Using it on true tells us true is of type bool. You can set 2 as type int instead of the default nat using the same notation. We can also create a variable by writing def variable name, specifying its type, and then defining its value. We can check this variable and see that the type is nat. Another command eval is used to view its value, which is 2. If I try to assign hello to this variable, an error is thrown with a clear message. If I leave the value as a blank, Lean tells me what type it expects, which in this case is nat. From these, I can define more complex types. The product type nat cross string is a pair of a nat value and a string value. We can check its type and evaluate its value. If I assign a bool value to the right side, error. If I leave the second value blank, Lean tells me it expects a string value on the right. The function type nat2string is a function that takes a value of type nat and outputs a value of type string. In this case, it will simply output a string with the next number. If I change the output value to a bool type, error. If I leave the output blank, len tells me it expects a string value output. We can check the function's type and evaluate it on an input nat value. If I give it a bool value input, error. If I leave the input blank, len tells me it expects a nat value input. So how can we connect these two ideas? In normal math, numbers, sets, functions, propositions, etc. are part of the theory, but proofs lie outside it. However, if we are to write a proof in len, it must be an object, which means it must have a type, and it can be stored in a variable of its type, which you can think of as the proof's name. What should a proof's type be then? Let's try to construct proofs for different compound propositions: implies, and, exists, and for all. If 14 is even has this proof, and 2 divides 14 has this proof, then the proof for even 14 implies 2 divides 14 assumes the proof for even 14 is given and creates the proof for 2 divides 14. It's like a function from one proof to another. If the first two proofs have types A and B respectively, then the function proof for the implication statement will have type A arrow B. This proof function will take in a proof of even 14 and output a proof of 2 divides 14. If I give it a proof of even 12, it will reject it, as the input type must be A, which only the proof of even 14 can satisfy. Clearly, proofs of different propositions must have different types. So what if we made the propositions themselves as the types of the proofs? That sets A to be even 14 and B to be 2 divides 14. This is the big propositions as types idea. Just like how nat is a type with natural numbers as values, proposition 1 plus 1 equal 2 is also a type with its proof as its value. False propositions like 1 plus 1 equal 3 will also be a type, but it'll be empty as it has no proof. Essentially, empty propositions are false, while non-empty propositions are true. This can now be read as PF is of type 1 plus 1 equal 2, or PF is proof of 1 plus 1 equal 2. We can also make the proof variable name more informative. The axioms themselves will be types too, with values A1, A2, etc. in them. You can think of these values as the declaration that these axioms are true. The axioms are non-empty by default. If mathematics is a rich landscape with rivers, then the sources of those rivers are the axioms. Whatever places they fill up are the true propositions, while all the false propositions are left dry and empty. Going back to the chess analogy, the positions would be types. The starting position type has a value start by default. Any other position types would either have a proof value or be empty. Let's focus on this true position type. Define this variable to be the proof of this position and let its value be start. The type checker raises an error because the start's type does not match. It's like assigning a string value to a nat type variable. We can apply a function to move the c pawn, another to move the knight, and the final one gets us the correct type. This term is proof for this position and is stored in this variable. Now, finding a proof from the start may be harder than assuming a position nearby and proving from there. We can do this by defining this variable to be the proof of the final position while assuming h to be the proof for the position before it. The value is now the move g3 applied on h. This same concept applies to math as well, so we'll be focusing on the easy part from now. Declare PF1 to be the proof for 2 divides 14, which we'll assign sorry, which means sorry, I don't have a proof. Assume we have HF as the proof for even 14 implies 2 divides 14 and H1 as the proof for even 14. Since HF is a function that takes a proof of even 14 as input, I can give it H1 as input. Replace sorry with let H2 be HF applied on H1. The output H2 has type 2 divides 14, which is exactly what we need. So let that be the value of the proof. The type checker finds no errors, which means it's correct. We've covered an imply statement. Let's look at an AND statement. If 2 greater than 1 has its proof in this variable and 1 plus 1 equal 2 has its proof in this variable, then 2 greater than 1 and 1 plus 1 equal 2 must have both the above proofs together. It's like a pair value of the two proofs. This pair value proof must have type 2 greater than 1 cross 1 plus 1 equal 2. Declare PF2 to be the proof for 2 greater than 1 and 1 plus 1 equal 2, with sorry for now. Assume we have H1 as the proof for 2 greater than 1 and H2 as the proof for 1 plus 1 equal 2. The proof for the AND statement should just be a pair, so let's make a pair with two blanks. Lean tells us that the left blank must have type 2 greater than 1. Do we have anything like that? Yes, H1. The right blank must be a proof for 1 plus 1 equal 2, which is H2. That's the proof. Moving on to an exist statement. If 14 equals 7 plus 7 has a proof, then there exists a k of type NAT such that 14 equal k plus k has a proof which lets k be 7 and shows the proof that 14 equals 7 plus 7. It's like a pair value of 7 and this proof. This pair value proof must have type NAT cross 14 equal k plus k, where k depends on the NAT value here. Declare PF3 to be the proof for there exists k of type NAT such that 14 equal k plus k. Assume we have H as the proof for 14 equals 7 plus 7. The exists proof is just going to be a pair of the NAT value 7 and H, which is the proof that 14 equals 7 plus 7. No errors, and that's the proof. Lastly, we have a for all statement. If this infinite list of propositions has this list of proofs, then for all n of type NAT, n plus 1 is greater than n has as its proof all these infinite proofs, as it needs a proof for every natural number. We can generalize the above as for some particular m plus 1 greater than m with this proof. The for all proof now becomes a function from every natural number m to the proof that m plus 1 is greater than m. If I input 0 into this function, I will get the proof that 0 plus 1 is greater than 0. If I input the NAT value 5, I will get the proof that 5 plus 1 is greater than 5. Essentially, for all natural number inputs, the output will be a proof for each. This function value proof must have type NAT arrow m plus 1 greater than m, where m depends on the NAT value here. Declare PF4 to be the proof for 5 plus 1 greater than 5. Assume we have HF as the proof of for all n of type NAT, n plus 1 is greater than n. Since HF is a function that takes in a NAT value, we can input 5 in it. Let H be HF applied on 5. The output stored in H has type 5 plus 1 greater than 5, which is exactly what we needed. That's the proof. This is the essence of the Curry-Howard-De Bruyn correspondence. A proposition is a type. A proof for a proposition is a term of that type. A true proposition is a non-empty type. A false proposition is an empty type. An imply statement is a function type. An AND statement is a product type. An exist statement is a dependent product type. A for all statement is a dependent function type. These new ideas can take some time getting used to. I'll put links in the description for further reading material if you're interested. Subscribe for more such content.